In 1901, the Nobel Prize was awarded for the very first time. The pressure on the committee was immense. Their inaugural choice would set the standard for all future laureates. They needed a true pioneer whose work had fundamentally reshaped our understanding of the chemical world, a figure of undisputed genius. In chemistry, that honor went to Dutch scientist Jacobus Henricus van 't Hoff. He was recognized for his extraordinary discoveries of the laws of chemical dynamics and osmotic pressure, concepts that opened up entirely new frontiers in physical chemistry and laid the groundwork for generations. Today, we'll explore the man behind the prize, who he was, the revolutionary ideas he championed, and how his work still shapes science today. Jacobus Henricus van 't Hoff was born in 1852 in Rotterdam, Netherlands. His father was a physician, but young Jacobus was equally passionate about nature and poetry. This blend of analytical thinking and creative imagination would become a hallmark of his work. He pursued chemistry in Leiden, then traveled to Bonn, Germany, to study under the legendary August Kekulé. This experience with a giant of organic chemistry was invaluable, shaping his understanding of molecular structures. What truly set him apart was his curiosity about the connections between chemistry and physics. In the 19th century, these disciplines were largely siloed. Van 't Hoff, however, saw them as essential for a deeper understanding of matter. He was a true pioneer, one of the first to systematically merge these fields, laying the foundational principles for what we now call physical chemistry. Then, in 1874, at just 22 years old, he proposed a radical idea. Carbon atoms and molecules aren't flat, but have a three-dimensional tetrahedral arrangement. This concept was the birth of stereochemistry. The idea was met with skepticism, but it brilliantly explained a puzzle. Why isomers, molecules with the same atoms, could have different properties. The ridicule didn't deter him. This was his first taste of challenging the status quo, a bold move that would define his career. Now let's explore the discovery that won him the very first Nobel Prize in chemistry. Van 't Hoff focused on osmotic pressure. This is the force generated when a solvent, like water, moves through a semi-permeable membrane, a barrier that lets water pass but blocks larger particles like salt. This movement from a dilute to a more concentrated solution creates a measurable pressure. This isn't just a lab curiosity, it's a fundamental process of life, explaining how plant roots absorb water. He noticed something incredible. The dissolved particles in a dilute solution behaved in much the same way as molecules of a gas. This was a radical leap, that dilute solutions act like gases. He proposed that just as gas pressure depends on temperature and the number of molecules, so too does osmotic pressure, following the very same physical laws. He even wrote an equation for it. Pi times Vi equals nRT. This is a direct parallel to the ideal gas law. Let's translate. Pi is the osmotic pressure, V is the volume of the solution, N is the number of moles of solute, a way of counting the particles, R is the gas constant, and T is the temperature in Kelvin. Why was this so powerful? Before Van 't Hoff, determining the molecular weight of large molecules like proteins was a nightmare. Standard methods involved boiling, which destroyed the molecules being studied. Van 't Hoff's law provided a gentle, non-destructive alternative. By measuring osmotic pressure, scientists could accurately calculate the mass of huge molecules, opening the door to modern biochemistry. The committee also considered big names like Marcellin Berthelot from France, known for thermochemistry, Wilhelm Ostwald, who worked on chemical equilibrium and catalysis, Svante Arrhenius, father of the theory of electrolytic dissociation. The competition for the first ever prize was fierce, but they chose Van 't Hoff because his work bridged physics, chemistry, and biology. Exactly the kind of broad, unifying science the Nobel Prize wanted to celebrate. The scientific community welcomed the decision. His theory was clear, elegant, and backed by strong experiments. Some physicists were skeptical at first. They didn't like applying gas laws to liquids. But over time, as experiment after experiment confirmed his ideas, the skepticism faded, and his theory became scientific law. Even today, Van 't Hoff's equation is taught in chemistry courses worldwide. His work is foundational for developing pharmaceuticals, formulating safe IV solutions in medicine, and understanding food preservation. He also inspired future Nobel laureates, including Arrhenius and Ostwald, to continue blending chemistry with physics, the foundation of physical chemistry as we know it. Jacobus van 't Hoff wasn't just the first Nobel laureate in chemistry, he was a scientist who proved that connecting disciplines can open entirely new frontiers. His intellectual courage to see patterns across boundaries changed science forever. And perhaps that's the real legacy of the 1901 Nobel Prize, not just rewarding great discoveries but setting the expectation that science should break boundaries and bring worlds together.